Hi, I'm Muhammad Usama, and I'm going to talk about Citus Cluster Scaling. The recent version of Citus landed two new enhancements in this area, and I'm going to talk about both of these, how you can leverage those, and what they are all about. Okay, so let's get started. The title is Move Less, Move Faster. Two halves to the title, and I hope by the end of this talk, you'll understand exactly what each one means, and more importantly, why putting them together changes how you scale up Citus cluster and what benefits do you get from that from these. Why this talk? So there was a customer of ours. I'll spare you the name. Runs a four worker Citus cluster and about 18 to 20 terabytes of data. All was good, healthy cluster, happy customer. Then they decided, why don't we add another worker node? So they provisioned a new node line and start rebalancing on a Friday night and went home. Monday morning when they came back, rebalance was still running, and Monday evening it was still running and finishes sometimes in the Tuesday. Now, if you think like 18 to 20 terabyte is really modern on the really on a modern hardware is nothing. Like it would have taken like few hours max or a day max, but for Citus it took like 3 or 4 days, and so the question is where the time go. Definitely, the data was not a bottleneck. The machinery that moves the data was the bottleneck, and this talk is what we did to get rid of this issue. Okay, so here's the overview of the talk. The talk consists of three parts. The first one is move faster. The second one is move less, and then in the third part, I'm gonna put these all both together, and we're gonna see how you can utilize this. What are the knobs you need to change? What are the options you have? And okay, let's move on with the talk then. Before anything, let's start with a quick Citus refresher in case you only heard about Citus on a coffee break or something and you do not know, or yeah, you heard the name, but you do not know what it is all about. So, in the nutshell, Citus is a Postgres extension, and that turns Postgres into a horizontal scalable cluster. As you can see in the diagram, there is a coordinator at the top, which is just a normal standard Postgres with a Citus extension on it, and then there are n workers, and again, all these workers are simple Postgres with Citus extension. Basically, Citus is a huge extension, but there are three main concepts to keep in the mind. And the first one is the distributed tables. So the distributed tables are sharded across all the worker nodes. And then the second one is the reference table. Again, that's a small lookup table, or I should say, it should be a small lookup table, but yeah, they are tables which has exactly one shard, and they are copied across all the nodes, like exact same copy. They are replicated across all the nodes. And the final one, co-location groups. So the co-location group is a set of distributed table that shares the same distributed column, and their shard lives together on each node. The reason to have these reference table is our collocated group is to make sure our joins works, uh, uh, like speed up the joins. Okay, right. So before we discuss the scaling and related improvements, let's quickly look at what scaling actually means in terms of the Citus cluster, of course. Otherwise, everybody knows what the scaling is. So when you add a new worker node to a Citus cluster, that worker node is pretty much empty at the start. And we need to put that node to work by moving some of the shards from other nodes to that new worker node. To do that, Citus run a rebalancer. The purpose of the rebalancer is to move 1/n shards from all the cluster to that new node, or to that new empty node, you can say. Yeah, that's what rebalancer. Under the hood, the rebalancer does three main things. First, it copies all the reference tables to the new worker nodes. As I said, like reference table has to be replicated on all the nodes. and then it moves 1 over n. N is the number of nodes, 1 over n distributed tables to the shard. And finally, a cutover step that flips the placement metadata and drops the old shard placement and old shard data from the old node to and mark that placement that it's now present on the new node. So that's pretty much what the rebalancer is. Okay, so that was a quick walkthrough of Citus, just a very brief intro about it. So the now let's move to the first part. The first part is about making the rebalancer parallel, and this is about moving fast. If you have to move, you have to move fast. This is the anatomy of a slow rebalancer. Let's see where the time went in our customer's rebalancer job case that I told you about. It took 3 or 4 days to complete. So almost about a quarter of the time, if you see the first 25%, a quarter of the time it was taken to by the reference table copy, and the rest of the 70% was taken uh, for to moving the shards from the existing nodes to the new node. The 5% is again just like miscellaneous things like creating the constraints and metadata cleanups and stuff. That's not matters. And guess what? Like when this all was happening, the network, the CPU, they were mostly idle. The wall center of the Postgres, only one was busy at the time, and rest of them ideal. So they have the pretty much uh, all the system resources, yet like Citus was not utilizing it and utilizing those. So that one rebalancer job took like $100 maybe. So okay. So why was it serial? And why all the shard and the reference tables move in serial fashion? Like, what is the reason behind it? So there are actually three main reasons. First, the first one is a very conservative locking. Actually conflicts the locking which we take to move the shard. It technically conflicts with all other operations on this particular shard or on this particular co-location group. So that's the first reason why the all the rebalancer thing, like all the shard movement, this was serial. And the second was within the co-location group, shard moves sequentially as well. And again, partially because of locking and partially because of design. And the last one was the reference table copy ran inside a single transaction on a single connection. So as part of enabling a two parallel rebalancer, we need to fix each of these underlying issues with the existing rebalancer approach. So let's move on to this. Okay, the fix number one. It is about moving reference tables in parallel. And we need to copy reference table to a new node before we can start moving any distributed shards to that node. And the reason for that is we can have constraints on reference table, like your distributed table could have foreign key or other constraints on the reference table, because the reference table exists on all nodes, so you can have these constraints. Second, like the reference tables could have their constraints within themselves as well. For example, I have two reference tables, they could be connected to each other by foreign key or maybe or some other constraints as well. So the first step of setting up any node or rebalancing is to move the reference table, and then after that we'll start moving the actual shards or the distributed table shards. But but moving the reference table in parallel is not easy, because again, as I told you, like these reference table could be interdependent on each other. So how we achieve the parallelism for to move the reference table in parallel? So so to achieve that, we actually divide this thing into two steps. First, we'll gonna copy the data of the reference tables all in parallel, and then defer the constraint creation for the later step. So once all the reference table, for example, if I have 5 reference table, I'm copying all in parallel, and once all the reference tables are already on the other node, then we start creating the constraints. And So so yeah, this is the first fix which we did to kind of parallelize the overall rebalancer. and and in case you're thinking why moving reference table in parallel matters, like because like reference table is supposed to be small, but the reference table are actually small in documentation, but in actual world they tends to be bigger. I have seen reference table like 40 GB, 50 GB each. So yeah, parallelize moving the reference table is a real beneficial for overall performance of the rebalancer. Okay, so the second fix. Once the reference table move bottleneck was removed, the next fix was to to fix the locking issues or bottleneck, the over conservative locking we talked about. So the first thing was we set up the goal. What is the goal? What we want to achieve? So basically, we have two kinds of operations in Citus, on a collocation group or on a what you can say distributed table. One is the structural changes like shard split, promote a clone, create a new distributed table, or changing the layout or changing the schema. So these are kind of a structural changes that that is allowed on the distributed table. And these structural changes must remain serialized against the shard move. So you do not want this like you're doing a structural change and moving a shard at the same time. So that's pretty much not a good idea. And the second type of operations are placement move operations like shard move, shard copy, which we do it in the for the rebalancer. And so we should allow these multiple such operations on a different shard to happen in parallel. So they should not conflict with each other. The problem with the existing rebalancer was like it was treating both of these kind of operation as the same kind in the same way, and it was using a over conservative logs to block. So if any of the structural change operation or the data move operation was going on, it will the other one will get blocked. So so this was the first fix we want to do. And so how did we do that? So uh, this is a table which shows like what changes we made to the logs. So this is I'm not gonna go into the detail of each and every log. So but the overall idea was to remove the overarching logs that serialize the independent moves, and use a lock mode that are not self-conflicting for the moves, while they should be conflicting with the other operation, with the structural operation. So that's what we did. And the 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 takeaway was like serialize the dangerous case, yet let the independent shard moves run in parallel. So this was about the locking the improvement which we did. So after these locking improvements, so this is the net effect. Like the like move like now we can have two moves run in parallel. Like you can move shard 1, shard 2 in parallel, and even if they shard both of these shards are belonging to the same co-location group. And again, the shard belonging to different co-location groups were allowed, somewhat allowed in previously, but now not. But yeah, we have enhanced that too as well. But at the same time, while we want to block the DDL changes. So in the end, the bottom line is the same operations are still mutually exclusive when they need to be. And the only thing we allow as part of this change is to move versus move. Like that should not be conflicting. And this is exactly what is required for the rebalancer. So now let's come to the third fix. Like the third one was this is the last piece of the puzzle. Like with the logs fix, with the rebalancer, and with, like we can now move the reference table in parallel as well. So the last thing is to orchestrate all of this. So what we do is like we copy the reference table in parallel, and then once all the reference tables are copied, we apply the constraint. And once the constraint part is done, that means all the reference tables are already on the new worker node. Then we start moving the shards in parallel. So the part is like the Citus already have this background task framework we didn't, like, as part of this new enhancement, we didn't build it. So the only thing which we did is like smarter scheduling, like so that like we achieve the best throughput out of it. Okay, so again, like for this parallel rebalance, we haven't added any new UDF. Same Citus rebalance start UDF, which is listed in the slide. It now accepts two new optional parameters: parallel transfer collocated shards and parallel transfer reference tables. Right, these are two new arguments which is now allowed in this in this UDF, and I think they are self-explanatory. And by default, they are off. So like so you do not get any surprise if after upgrading to the latest version, and just in case, turn flip this off on when you actually need it. Yeah, before I move to move to the next part, so uh, a word about shard transfer mode. Okay, why I want to discuss is basically shard transfer mode, the same UDF which we discussed in the last slide. It also accepts the shard transfer mode argument, and it can have either force logical or the logical or the block, right? So these are two types of arguments that it can get, and the force logical is the one where that after copying the initial data, do a catch up via logical replication before making a cutover. The good thing about this mode is, excuse me, sorry, mode is writes stay online. Like the writes on the source shard is not blocked for almost the whole move, only for the very small cutover time that they gets blocked. And On the flip side, the replica identity is required on the tables if you want to use this forced logical mode. And the second one is the block writes. As the name suggests, on the other hand, like it blocks all the write operations on the source shard until the whole of the shard is copied to the destination. Uh, the reason I want to mention this is like the force logical mode, the first one mentioned in the slide, is the where the new locking helps the most, primarily because the locking fixes the area and the logic which is used by replication for the shard replication setup for moving the shard in the logical manner. And the block write also have this the benefit, but rather the benchmark, like the internal benchmark which we did was like at least 26 to 30% improvement when we are using the force logical to move the shards between the older version and the new Citus version. So let's talk about what actually gets faster and where the wins come from. So look, if you look at the timeline on the slide, the top bar is the old behavior reference tables, one after another, then shard moves and one at a time. And the bottom shows the new behavior reference tables, overlap, and multiple shard moves run side by side. So three things drive the win, like in this. First, the reference table copy is now one task per reference table in parallel. The more reference tables you have, the bigger the relative wins are. And second is the distributed shard moves run in parallel across co-location groups. Again, as soon as more than one move can run in parallel, you start gaining the time. And although the constraint and the cleanup, which I mentioned, like they are done in the serial, but still they take the very small amount of time. So the major chunk of the time is gained by parallel moving of reference table and the shards of distributed tables. Okay, so this is the thing. Like parallelism is again not free, and there's a point past which adding more executors stop helping, and maybe sometime it degrades the performance. And so this is a very important things to think to keep in mind. So what if you see this curve, like why it plateaued or flats on after sometimes. So the thing is, so the bigger the data set gets, the parallel is like and you have more parallel workers moving the data. So there comes a time when it's the CPU or the network, they started to become bottleneck. So before that time, before that point, like you keep gaining the performance benefits, but once disk or CPU or network, these things started to become a bottleneck, then there's a possibility like start seeing a degraded performance or at least the plateaued performance. So you need to be careful, like how much parallel workers your setup can take or should have. Okay, so okay, before moving to the next part, let's talk about some caveats. Like if you have one giant shard that dominates the wall time, the parallelism will not help. And as you know, like each move adds a wall sender, a decoder, and a replication slot, or and wall sender CPUs. So you need to check like what's your max wall sender setting, max replication slots and setting. And again, you have to keep in mind like how much of these your system resources can support again. So this is the second point. And one more catch is the like locking sign. Logical moves only works on the table with the replica identity. So enabling the replica identity means like more walls get generated. And yeah, so again, though you get a big win with the replica identity, again that's a trade-off you get from the setting the replica identity on any table. And finally, I think, yeah, if your network gets saturated, like then yeah, you'll not gonna get performance. Or even like you may start getting the performance for your rebalancer, but you start hurting the regular workload performance. So all these things, like do keep the headroom for max connection and other settings, and carefully configure these. Okay, so now let's move to the second part, which is move less. We have just done with the uh, move fast part. Now the second part is about the uh, move less. So so if you see like if you want how the data is moved by the Citus, um, how Citus move data is like it selects the table one row at a time, and sends that single row again one row at a time to the destination. And this is a Postgres speed. Like you cannot help it. Like because like the file has all the tuples, but again there could be dead tuples in there. There could be non-visible tuples in that. So all we can do is like we can run a sequential scan on a table, and then send every row on the other side. But if you step back and you can look, like there is another way to send the data on the other side, on the new node, and that is a PG based backup, or a disk snapshot, or a physical copy. Like you can take a physical copy of the data directory, and then just you can just ship it over to the new network. But that does not work as it is. Like you cannot like kind of ask Citus to do that, like read the file from the data directory, and then just ship it over to the other. So 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 there are two ways to like kind of send the data on the worker side. One is Postgres speed, and other is a disk network, or the network speed. So this is what the second thing. Yes, like this is the replica to the worker. So the idea is, rather than sending one row at a time, why can't we just take the backup of the existing worker, and restore that backup to start a new worker. So by doing this, what we can do is like rather than starting a new worker starting as an empty slate or a blank server, it starts with a replica of the existing worker node. And this is what the life cycle of the worker looks like. And this is about the second feature which we added, which is like adding node using a snapshot of the existing node. So it is the first step is you get a replica of the worker, and you can take it like you use take the replica from using four ways. You might use the existing HA replica. You can use existing stored base backup, or you can take a new backup on the fly, or you can just take a disk snapshot. Once you have this restored on the machine, just the second thing you need to do is Citus add clone node. This is a UDF which attaches that replica of the worker to the Citus. And once that is done, the third is pretty much optional step, which is get snapshot based node split plan. So it just gives you the plan. We're going to discuss it in the next slide, like how the plan looks like. And once all these things are done, just call this site as and promote, clone, and rebalance UDF, and it will make the replica as a new primary. So this slide discuss what is done in this the last UDF we talked about in the last slide, Citus, promote, clone, and rebalance. So this UDF has 6 steps. The first one is it takes exclusive lock on the source worker, and it blocks all the writes on that worker. And reason it needs to do that is to make sure that the replica it catches up with the source worker node. And but yeah, that is a very small time. Like if you just taken a backup, it could be just matter of few seconds. That's about it. So once the replica or the clone, which we call it in the Citus term, which cached up with the original primary, the next thing it does is it promotes the replica to become using PG promote, it becomes a new primary server. And once that is done, the fifth step is flip the metadata switch. What that means is it marks this clone as a new worker node. Like now the previously added clone becomes a worker node for the Citus, and the last step is rebalance. We're going to discuss the rebalance right now. So this is the rebalance. Previously, if you remember what we were doing in the rebalance, we were moving the shards from the existing workers to the new worker, which was taking quite a lot of time. Now what we do is, because we started with a clone which is exact copy of the existing worker, for example, in the first, like S1, S2, S3, S4, like these shards exist on both source and the clone, and they're exactly the same copy, because we made sure just before anything that they are the clone is not lagging behind. So instead of copying, now we are deleting the shard. So we're gonna delete S3 and S4 from the source, and S1 and S2 from the clone. So now just by dropping and deleting the shards, we did the rebalance. So this is very fast. And this is just a example of like what the snapshot plan gives you the output. So when you call the get snapshot based node split plan, between primary and the clone, it gives you which shard will stay on the primary node and which will be moved to the clone node. And once you execute it, uh, shards which is supposed to be staying on the original primary will be deleted from the clone, and the other ones will be deleted from the primary node. Again, this is just what I just described. This is just some visual representation of difference between the traditional and the snapshot based node addition, like how they are both different. In the first one, the traditional one, we are moving the shard. We are starting with from an empty node, and we are moving the data from the existing workers to the new one. But with this new snapshot based node addition, what we are doing is we are starting with the clone of the node rather than the empty node, and then we are deleting. So the second one is very fast. I'm just running out of time, so I'm gonna jump to the last part, which is very just a very single or two slide long. So which is how we can utilize these two. Like pick the right approach. So this is if you're adding the capacity and you already have the H replica, even if you don't have the H replica, but you have the large data set, just go with a snapshot based split rather than doing a empty node, starting with the empty node and doing a rebalance. And if you are adding a capacity and with the database data set is very small, or you need to drain a node, or like, then a parallel rebalance is a good. But if you're going to double the number of node, like going from 4 to 8 nodes in, and you have a very small maintenance window, like the only option is that go with the snapshot based node addition for the heavy lifting, and eventually do the parallel rebalance. So yeah, these are just operation guidelines. I think we've just already discussed about these. Like, these are the knobs, like max background task executors and max share pool. These are the things which really affects the performance of parallel rebalance. And you need to be aware of these, and you may need to find your own sweet spot for each of these settings. And in the end, like, it's just for the snap. Like, if you want to see like how going from 4 to 8 workers, what is the playbook, this is it. Like, these are just 6 steps. Take the backup, add it as a clone, get the snapshot plan, review it, do this, and then just call the Citus rebalance start, and then drop the replicant slot in the end, just to clean up the things. And yeah, that's about it. Thank you very much.